It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Dave Ansell.
Hi there.
And with Richard Van Norden.
Hello.
Now, coming up this week, we'll be finding out how scientists have discovered that it's possible to train a caterpillar, and what it learns as a caterpillar, it actually remembers as a moth. Also, how a strange force is at work in space, which is slowing down space probes. But what is it? And why environmentally friendly cars might be bad news after all, because powering them is going to use a lot more water. That's all on the way. Dave.
Thanks, Chris. Also this week, we're meeting the man who created the Ig Nobel Prizes, which reward science that makes people laugh, then think.
The Ig Nobel Medicine Prize was awarded to Dr. Francis Fesmire of Tennessee for his medical case report called Termination of Intractable Hiccups with Digital Rectal Massage. Is there anyone here who needs this concept clarified? Is there anyone here who has hiccups at the moment?
That's Mark Abrahams, who we're talking to later.
Thanks, Dave. Also on the way, we'll be hearing how sea cucumbers have inspired a new material which could be useful for brain implants. And there's our question of the week. We'll be finding out if cutting or shaving hair really does make it grow faster.
Thank you very much, Richard. It is, of course, our science Q&A extravaganza this week, so if you've got a science question for us to solve, or you just want to say hi, then do get in touch. So far, we're finding out why milk goes yellow when it freezes, and also what would happen if you launched a spaceship into a black hole, and that's assuming it's a spaceship that can stand up to the job. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Well, let's kick off first off, as we always do, with a look at some of this week's hottest science news stories. And this one caught my eye because, as someone who's a keen gardener, I absolutely hate caterpillars. They absolutely destroy half my garden. But there's a guy called Doug Blagiston who works at Georgetown University. He's got a paper in PLOS One, the journal this week, where he's shown that you can train a caterpillar, and better still, we say that elephants never forget. Well, it turns out the caterpillars don't either. What he did was to take some tobacco hornworm caterpillars, and he gave them small electric shocks at the same time as exposing them to a certain smell, and then demonstrated that when they'd gone through their chrysalis stage and emerged as a moth, then they could remember that when you expose them to that smell, they went away because they thought they were going to get an electric shock. Sounds a bit trivial, but why did he do this? Well, everyone thought that when caterpillars pupate, that basically a caterpillar's an eating machine. It takes in lots of energy and then it gets completely dismantled inside its chrysalis and re-emerges as this moth, and basically all the energy it's taken in is just used for that purpose. But actually, it turns out that it's much more complicated than that, and it can have these memories, and this explains why, for instance, that adult moths will go back and lay their eggs on the same plant that originally hosted their caterpillars, because they can remember. And also, he thinks this might be important for the purposes of evolution, because what you can argue is that if you have a plant which establishes a specific relationship with a caterpillar like this, it's much more likely to develop a relationship going on into the future with that plant, and if something bad happens to it in the future, then it will avoid that plant in subsequent generations. So this is a good way in which you might get the emergence of new species just because of this particular ability to learn and then carry on with that memory from caterpillar through into moth. So intriguing.
Has anyone looked, does they know any how it can remember this through, I guess the brain's turned to mush while it goes through the chrysalis stage, is it?
Well, that's what everyone thought, but clearly the nervous system isn't turned into what you call mush completely. Whatever the correlate of storing memories in the caterpillar brain is, or the nervous system, obviously connections between nerve cells, they're preserved enough that it can remember simple memories, like Pavlov's dogs, which salivated when he rang a bell. Well, this is the caterpillar equivalent.
I guess it makes sense. Now, for the last 10 years, physicists have been slightly puzzled by a mysterious force acting on their space probes. There have been various slight anomalies detected on how spacecraft move, which don't agree with how we'd predict them to move using Newton's mechanics or even Einstein's mechanics. Now, one of the first anomalies which was noticed was on the Pioneer spacecraft that visited the outer solar system during the 1970s, and it's still just heading off into space. There's a couple of these, and they seem to be slowing down slightly faster than we predict using our present understanding of physics. The effect's minute, about a 10 billionth as strong as the force of gravity on the surface of the Earth, but it is measurable. Now, this physics could just be just some little tiny trivial thing we don't understand, like a little tiny gas leak, or something to do with how it's radiating heat unevenly, which we don't really understand. But now a team from the Jet Propulsion Laboratory in California have found another anomaly which seems to appear when spacecraft do a flyby by Earth. This is where, if you want to get a spacecraft to go a long way away, they tend to fly from Earth to Venus, then back to Earth, then possibly off to Jupiter, because each time they do that, they can gain a bit more energy and go slightly faster. For example, they had a look at the NEAR spacecraft, which was on its way to visit an asteroid, and it left moving. It was only 13 millimetres per second slower than it should have done. And the Galileo probe, which was off to visit Jupiter, was sped up by about 4 millimetres a second, which is a minute effect when they're actually moving kilometres a second.
It's minute, but in terms of it being quite a local and quite a short-term experiment, that's quite a lot. So given that we thought we understood how forces work and we thought that Newton and Einstein between them had it worked out, what's going on?
Well, they're not entirely sure, but a guy called Frank Jordan and his team who found this out have been looking at the different space probes, how fast these anomalies, how big these anomalies are, and he's worked out a formula which seems to suggest that it's all to do with whether they come in and out at the same angle to the equator. If they come in and out at the same angle to the equator, nothing happens. It's absolutely boring. But if it comes in on the equator and leaves off towards the North Pole, then you get a big effect. Now, he doesn't really, this doesn't tell you what's going on, but it does kind of give an indication it may be something to do with the Earth rotating. Einstein's theory of general relativity does have an effect which should be to do with rotating objects, but that should be much smaller than this. So either there could be something really trivial going on we don't understand, or there could be some really interesting new physics.
What about the point you made earlier about probes leaving the solar system altogether, and those then seem to be showing these effects too? So what's rotating there then?
It could be just all of the mass in the solar system, the sun and the planets, and just everything's rotating. It only seems to be an effect which is noticed by things which aren't in a bound orbit, orbits which are disappearing off to infinity.
So an interesting observation. How are we going to get to the bottom of it and solve the problem?
I guess by just looking at more and more probes, tying down what the formula is much tighter, and that will give us a better idea of what could be possibly causing it.
Oh, thanks, Dave. Well, I wanted to bring up this weekend a very interesting study saying that electric cars, which I always thought were very eco-friendly, it turns out they could really stretch scarce water resources. This is research from Michael Weber and Kerry King from the University of Texas at Austin. And they say that if you run a car on electric miles rather than driving it on gasoline or petrol, it uses up 3 times as much water.
But why should it use this much more water? Where's the water going? What's it being used for?
Well, the key is you've got to remember electric cars are being charged up from the electric grid, and that power's coming from thermoelectric power stations, and those power stations are using a lot of water as a coolant.
So this is coal, gas, things with cooling towers?
Exactly right. The big cooling towers that you see churning out water vapour into the sky, that's the water that's being evaporated and lost in the local environment. Now, we've already seen droughts in Southeast America and Australia causing a few problems for power stations, which have had to dial back, a bit concerned about loss of amount of local water. And basically, Weber is saying that if we move wholesale to electric cars, we're going to see much more stress on those power stations. Will areas that are accustomed to drought be able to take it?
So we basically have to plan ahead, not for global warming, but for also Earth drying because of using all this extra water.
Well, this is really a lesson that we need to plan ahead for everything, that we shouldn't be too, we've concentrated on
easier said than done,
the security of our energy supply and the carbon cost, but we've got to think about the water as well. And you can't take your decision about energy, how you're going to power your car, without thinking about water as well, which is something that's been neglected.
I guess the other option is to build all your power stations on the coast, because we're not going to run out of seawater in the near future.
Absolutely. Then how are you going to get your electricity into the middle of America? And then you've got to start thinking about that. However, if you move to solar power generation, then you might be looking at a less using up less water to create your electricity.
OK, well, thank you, Richard. That's certainly food for thought, isn't it? Just to finish, there's an interesting study come out this week. It's been done by Jennifer DeBose, and she's at UC Davis in America. And she's found a really interesting chemical that attracts fish to coral reefs. We covered about 6 months ago or so a study which showed that if you release juvenile fish into the sea, they can often 30 or 40% of the time find their way back to the reef that spawned them. No one really understood how, so this might be part of the reason, but it's also a really intriguing way in which coral reefs protect themselves, which is that there's a chemical they've been looking at, and it's called dimethyl sulfonopropionate, and that's why it's called DMSP, because it's difficult to say and life's too short. But where it comes from is marine algae, so small plankton and marine algal plants that grow on coral. When they get grazed by other microorganisms and other animals, they activate an enzymic pathway that produces this chemical, and it goes out into the water, and it turns out it attracts fish. It doesn't just attract any fish, it attracts fish that eat the things that are eating the marine plants. So it's a way in which they're attracting, or it's a sort of chemical distress signal which the marine plants put out, which then brings the fish in and gets rid of the things that are eating the plants. And the way they proved this was they had a big beaker of this material which they released into the sea, and next to it they had another one with just distilled water being released into the sea, and they looked at how many fish flocked up the gradient of this stuff diffusing out of the tank into the seawater, and they actually found about 4 times as many fish flocking towards this stuff as they did around the water, which shows that the fish are attracted to it. Exactly how they don't know, but it's certainly an interesting example of how you can bring in fish that will eat plankton that do this grazing, and therefore the coral defends itself. Not the coral obviously itself, but the algae that live on the coral and the other zooplankton.
So it's kind of good for both of them, because the fish gets some food and the coral gets to get rid of this annoying zooplankton.
I guess you could look upon it like that, yeah. It's The Naked Scientists with Chris, Dave and Richard, and we're talking this week about anything science. In a second, we'll be finding out from Samantha Smith about moonlight rainbows. That's coming your way, I guess, Dave. And also Connor wants to know about how much water there is on Earth relative to 1 million years ago.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
It's The Naked Scientists, and on the line now is Sam. Hello, Sam.
Hello there, how are you?
I'm very well, thank you. You've got a question for Dave?
Yeah, I'm not sure where to begin on this one. Okay, I was driving home one night. I work in Newcastle and I live in Carlisle, and I was driving home along the A69 one night about 6 weeks ago now, because it was a full moon, I remember that. And it had been a beautiful night when I left Newcastle, really clear skies. And on the way home, going along the A69, there was just enough rain starting coming from the west to be awkward enough to have to put my windscreen wipers on. And it was making a horrible smear across my screen. So what I saw at first, I thought was muck and stuff from the road smearing across my screen, because there was this sort of lighter crescent in the sky. Put my windscreen washers on, and it cleared away, and yet this thing was still there. And what I was looking at was basically a very precise, very thin crescent of what looked like lighter sky. I thought at first it might be clouds or something in the sky, and I was sat there thinking, what on earth is that? And then it came to me, it's a moonlight rainbow. And I thought, well, hang on, is that actually possible? And if it's possible, how does it happen?
Was it on the opposite side? Was the moon behind you or in front?
The moon was behind me. It was rising still, and I was going into the rain. So yeah. I was driving towards it.
So, yes, I think that is actually just a straight moonbow. It's exactly the same as a rainbow caused by the sun. So what happens is if you shine light on a little droplet of water, the light will sort of bounce around inside it, and when it comes out, different colours will come out in different directions. And so if you look at little water droplets in different places, you'll see colours different of these colours which are bounced around inside them. So if you look in different places, you see different colours and you see a rainbow.
Yeah.
Now, with the moon, it's a source of essentially white light, so you get exactly the same effect. But because it's so dim, your eyes won't be sensitive to the colour, so you'll just see a kind of bright, a sort of bow of brightness rather than of colour.
Yeah, it's sort of bright greyish white.
Yes,
yeah.
If you took a very, very, very long exposure photograph of it, or you had an image intensifier which worked in colours, then you would be able to see the colours, and it would look just like a normal rainbow.
That's really cool.
I think it is too.
Apparently they're quite rare. I was looking them up afterwards to find out if I had just been imagining things, and it seems they're quite rare.
Yeah, I think actually seeing proper rainbows, normally what people see is a ring which is around the moon itself, sort of maybe 22 degrees outside the moon, which is normally created by little ice particles, which isn't a true rainbow, but it's a similar sort of effect. It's refracting inside the ice particles instead, but your one I think is more rare.
That's brilliant.
Sam, you've seen something very unusual. Thanks for joining us on The Naked Scientist. Great to have you with us. If you'd like to join us on The Naked Scientist, you can email Chris at thenakedscientist.com.
Now, we've had an email question from Paul Dark from Billericay, and he says, Dear Chris and colleagues, my son Robert has been wondering about this question. When we freeze milk, it changes colour from white to yellow. Why is this?
Okay, the reason for this, Paul, is because milk isn't just a straightforward solution. It's not like dissolving salt in water, where one dissolves in the other. Milk is what's called an emulsion. It's a mixture of various things which are suspended in water. So milk is about 5% fat, and that fat is dispersed through the water as tiny globules. They're called micelles, and they're surrounded by little proteins, which have a fat-loving part to the protein and a water-loving end. And so the fat-loving part of the protein sticks into the fat and the water-loving bit sticks into the water, and this helps to solubilize or keep suspended the fat particles. Now, also in the milk are these things called caseinogens or proteins, because milk contains a lot of protein, because the idea of milk is to nourish a growing animal, and protein's what you need to grow more muscle and get bigger. So when you put your milk in the freezer, all of these things which are normally well suspended and kept separate begin to become very close together, because the freezing process means that the water in the milk, 95% of the water of the milk being water, forms big chunky ice crystals, and they don't want to have the proteins and the fat in them, so the proteins and the fat get squeezed out of the mixture, and they tend to form around this central core of ice. And so because you see all the fat in one place, it looks yellow. And if you look where butter comes from milk, of course, and butter's yellow. So that's where the yellow colour comes from. It's because it's all conglomerated in one place and you can actually physically see it. So you see this nice yellow colour. I hope that answers the question. Now, Dave, bit of kitchen science. What are we going to do this week?
Well, this week we've got a really simple kitchen science for you. All you need is 2 largish balloons and a little tiny piece of tubing. So a tube which is a bit bigger than the next of the balloon. So one thing I've found which works quite well is the lids of some marker pens which haven't got a little clip on them. They make a nice tube because they've hollowed them out so kids can't swallow them and choke. So what we want you to do with that is take the lid off your marker pen, or maybe a little piece of hose pipe or something like that. Put one balloon over the end of it. Okay, so that's a little bit more interesting than you'd expect. Okay. So
this is a deflated, you're just putting the balloon on deflated.
So just a deflated balloon over the end of it. Now I want you to blow it up so it just starts to inflate. So normally a balloon's very easy to inflate, very, very tiny first bit, and once the next bit's quite difficult, so you want it just starting to inflate. So maybe sort of about a third of its normal diameter, quarter of its normal diameter. So somewhere about there. Then twist the balloon up.
So you're just nipping it off so it can't basically deflate while you do the next bit, I suppose.
That's exactly right.
Okay.
And then put the other balloon on the other end of the tube. And I want you
I see. Okay, so what you've ended up with is a bit like a dumbbell you'd use in weightlifting or something. You've got a balloon full of air on one side and a completely deflated balloon on the other side.
That's right.
And what's the question?
What's going to happen when we untwist the inflated balloon? What's going to happen to the other balloon? And if you're doing it, see whether you can get the 2 balloons to be the same size and stay that way.
Intuitively, you want to say, it's just going to flow out of one and into the other. What's actually going to happen? I'm intrigued. So if you want to do this, very simple. Just get these 2 balloons, put some air into one of them, and put nothing in the other one. Connect them together with a thin piece of tube. We've used the cap of a marker pen because, as Dave says, they're drilled out. They've got a hole in them so that you can't actually physically choke on them. And then release the air from one and see what happens. If you can explain the science behind that, or you have a theory, you can email chris@thenakedscientist.com. We've got lots of questions coming up. We'll be finding out about the amount of water on Earth. We'll also be finding out about salt water and fresh water and how they come to be like that. Why are some bits of the Earth covered in fresh water and other covered in salt water? And we'll also be catching up with all of the latest from the world of chemistry with Mark Peplow.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
And Connor is in Tillingham. Hello, Connor.
Oh, hello.
Welcome to The Naked Scientist. What can we do for you?
Well, I was just wondering, actually, water on the Earth, is there more or less now than there used to be, say, 1 million years ago?
Well, in that sort of time frame, Collar, I reckon the answer is probably roughly the same. It does increase by a small amount. I think the stated geological figure is about 1 inch or 2 every 20,000 years or so, and that's extrapolated over the lifetime of the Earth. Most of the water we have comes in the form of comets hitting the Earth. When the Earth first formed, of course, there was a disk of stellar debris, which was basically the material left over from where the Sun formed, and out of that we condensed planets as planetesimals. They slowly aggregated more material material and form bigger planets, and the material left over was comets and other asteroids and other bodies which were out there in orbit. And comets are viewed as what are called dirty ice balls. They're basically lots of water with some muck and other stuff chucked into them. And occasionally one of them is going to cross the orbit of a planet, get drawn in by gravity and crash land. And so most of the water on Earth, we think, comes from comets originally. So given that they're not actually that common these days, but over the million-year timescale, I think probably the amount of water on Earth hasn't changed a huge amount, but I would add that it probably is increasing very, very slightly. What do you think, Dave?
There is also a mechanism whereby the Earth loses water. What happens is that in the upper atmosphere, you've got a bit of water vapour high up in the upper atmosphere, and it gets hit by ultraviolet light from the sun. That can split apart into hydrogen and oxygen. Now, this light hydrogen will tend to float up really high and then get blown away by the solar wind. It's a very, very slow process, but we are losing water, or losing the hydrogen from the water all the time. The oxygen will stay on the Earth because it's much heavier and tend not to get lost.
Same thing happened with Mars, didn't it? Because about 4 billion years ago, when Mars was about 500 million years old, it lost its magnetic field because the planet got too cold to have a liquid and then a solid iron core, and because that's how the planet generates its magnetic field, it could therefore no longer have a magnetic field. That meant that it was vulnerable to the solar wind, which was just plucking all of the gas, the atmosphere and the water from the planet, and it dried out.
And also to Venus, because Venus is very, very similar to the Earth, but has a much weaker magnetic field, which tends to protect it because it protects the Earth from the sun solar wind. And we think that the Venus at the moment is sitting at about sort of 500 degrees centigrade on the surface. And the big difference between Venus and Earth is the fact that Earth has a magnetic field which stops it losing water, whereas Venus has lost all its water, and it's really bad stuff has happened.
There you go, Connor. I think that wrapped that one up for you.
Oh, definitely. Thanks very much.
Pleasure.
Bye-bye.
Alan is in Cambridge. Hello, Alan.
Hello there.
Welcome to The Naked Scientist.
Thank you.
What would you like to talk about?
I'd like to talk about the difference between salt water and fresh water, i.e. seawater and spring water. Are they two different substances, or is one of them an artificially altered version of the other? And if the latter, which is the natural version? It occurs to me they have the same chemical formula, H2O, so I presume they're the same, and one of them is an evaporated version of the other, but I just wondered which was the original.
Yes, spot on, Alan. They are exactly as you say, the same chemical. H2O is water. The water cycle on Earth is why we have salt water and fresh water. What happens is that the energy from the sun hits the Earth's surface and the ocean's surface. Every square metre of Earth gets about 1 kilowatt of energy coming from the sun, so that's like having a 1-bar electric fire shining on it. That heat evaporates some water from the surface of the ocean. Water can leave quite easily, but the heavier elements and ions which are dissolved in the water find it much more difficult, so they stay behind. So what evaporates is essentially fresh water. This goes up and forms clouds. The clouds then drift across the ocean surface until they're forced to rise because there's, say, a mountain range or something. Because as the clouds are forced to rise, they find it much harder to hold on to the water which is condensing inside them, because clouds are just massive bodies of tiny droplets of water. The water rains down to Earth and falls on the land as fresh water, but as it percolates through rocks and runs into rivers, it dissolves small amounts of salts on the way through, becoming slightly salty in the process, but still not perceptibly salty. But as it slowly drains into the ocean, it carries those salts with it, so the sea picks up those salts, but then what leaves the sea is fresh water again, so the sea is continuously becoming slightly more salty. So why is the sea not becoming more and more and more salty forevermore? Well, the answer is it's become about as salty as it's ever going to, because it's now reached a sort of equilibrium position where if you add more salt to the sea, chemical reactions kick in and take it out again.
Right, so the seawater is the original or the basic version of water then, and what we have on the land is the altered one because of the because it's gone through the cycle you just described.
Absolutely right, Alan.
Right, fine. May I ask a very quick second one? I didn't give this to your researcher, but also I got wet today in Cambridge, with rained on, and I know you've answered this before. Is it better to walk through the rain slowly or to run through the rain? Where do you get most wet?
If the wind isn't blowing and the rain's falling straight down vertically, if you walk through the rain, it's constant rain, then you'll always walk through the same amount of rain. It will hit the front of you, no matter how fast you run. But if you go slowly, you'll get more that falls on top of your head on the flat surfaces than if you run. So running is slightly better than walking.
So there you go, Alan. But don't fall over, because if you fall over, you'll get very wet indeed.
And muddy.
Thank you very much for your call. Cheers. James is on the line. Hello, James.
Hello.
You're welcome to The Naked Scientist.
Thank you.
What's your question?
My question is, if you've got a dripping tap, which I did have a while ago, and it's dripping, say, once every 5 seconds or 10 seconds, how much water does that actually waste over time?
I've done a couple of very rough cut calculations on this. If you've got, say, a drip's about 1/10 of a millilitre, and it's dripping every 10 seconds, so that it's going to lose you about 36 millilitres an hour, which, if you multiply it up for the whole year, is about 315 litres a year. So sort of 1-2 baths full, depending on exactly how big your drip is and how big your bath is.
So I suppose really it's, if you've got a dripping tap, maybe like I did, I had several dripping taps in the house, it's really worth fixing them?
Yeah, definitely, because I mean, one drip every 10 seconds is really quite slow for a dripping tap. If you're talking, especially if you're getting into once a second or several a second, you're losing quite a lot of water.
Okay, thank you very much.
Especially when you look at what happened to the ceiling in my house when I had a dripping tap. Thank you very much for that wonderful question.
Thank you.
Thank you. It is The Naked Scientist with Dr. Chris, Dr. Dave, and also with Richard Van Noorden. He's joining us this week. Quick question for you, Richard. It says here, this is from Edward James. He's in Milton Keynes, and he says, if you're sitting in a car with the engine off and no heater or cooling fan on and the weather's dry or overcast but not raining, it takes ages when breathing normally inside the car for the windows to mist up. But when it rains, the windscreen mists up faster, even though there's no real obvious change in temperature. Why should that be?
Yeah, hi Edward. Well, I think there's sort of two things to think about here. Number one, when it's raining, the air's pretty moist, lots of water in the air. Even if you're sitting inside a car, the air inside your car is going to have a lot of water vapour in it. That's going to condense onto the inside of your windscreen. A second point to think about is that when it's raining outside, you've got cold water hitting the outside of your windscreen. Previously, you just had some air going over the windscreen. The cold water is going to take the heat away much better than the air does. And so that's really encouraging any water inside the car to condense on the windscreen, mist up your windscreen very quickly.
Thank you very much, Richard. I hope that answers the question. Quick one that's come in from James by text. He's in Cambridge. He says, when you thaw milk again, why does it completely reconstitute back into the milk? Well, the answer is it's all about energetics. In other words, when you actually bring the temperature back up, you've got molecules of water bumping into each other, and the consequence of that is that the particles of milk reform into these little micelles, which then spread out evenly through the milk, because that's actually the most energetically stable and favourable way for them to organise themselves. It is The Naked Scientists. It's Chris, Dave and Richard. And coming up, we'll be talking to Mark Peplow. He's from Chemistry World, and he'll be telling us how scientists have built an enzyme from scratch, and also how sea cucumbers could be about to inspire a new generation of brain implants. Plus, we'll be hearing from Mark Abrahams. He's the guy who founded the Ig Nobel Prizes, and he's over here in the real Cambridge, UK, because he's normally in Cambridge, Massachusetts. And he'll be talking about his Ig Nobel tour around the UK.
The Naked Scientists. Brought to you by thenakedscientists.com.
It's The Naked Scientists with Dave, Chris and Richard, and we are talking now with Mark Peplow, who is the editor of Chemistry World from the Royal Society of Chemistry. Mark, hello, welcome to the programme.
Hello, Chris.
So tell us about this first item.
Yeah, this, I think, is absolutely amazing. Scientists in America have managed to design and build a working artificial enzyme from scratch. Now, enzymes are nature's catalysts. They speed up chemical reactions in our bodies by tens of millions of times. We wouldn't work as living beings without enzymes. Basically, they're blobby proteins with a cavity in them that's perfect to fit chemicals that are involved in reactions. It brings them together in the perfect way to speed them up. Now, you can hijack these to do useful chemistry. For example, an enzyme in yeast turns sugar into alcohol in beer.
It's very handy.
But what about non-natural reactions? What happens if that reaction that you want to catalyse doesn't exist in nature? Now, normally, chemists use things like metals or metal compounds to do that, but it would be much better to be able to persuade bacteria to actually do these reactions for us. But to do that, you need to make your own enzymes. And now Lin Jiang and colleagues at the University of Washington Seattle have done just that. They made a computer model of a particular reaction called a retroaldol, and they designed an enzyme to fit around it. Then they actually made 72 similar versions of this enzyme in the lab. They found that 32 of them worked, and the best one speeded up the reaction by 10,000 times. Now, that's still 1,000 times worse than what you see in nature, but it proves that you can actually make these things from scratch, and it's exactly the sort of thing that if Craig Venter gets his hand on it and puts it inside one of his artificial life forms that he's promising to unveil next year, one of these artificial bacteria, this is exactly the sort of thing that you could put into that system.
It just goes to show that if you actually borrow from biology, nature spent millions of years getting things right. So if we apply the same concepts nature does and just do it slightly differently, you can actually come up with some pretty elegant solutions.
That's right.
And exactly in the same vein, sea cucumbers are inspiring a whole raft of new materials.
Yeah, this is a lovely little story, actually, that came out this week. Sea cucumbers are they're a relative of the starfish, and they graze on the ocean floor for carrion. When they're startled, they can become rigid in seconds, basically because they can control the collagen fibres that are in their skin. And now scientists at Case Western Reserve University in Cleveland, Ohio, have used this as inspiration to make their own material that does exactly the same thing. They made nanofibres of cellulose. These are thousands of times thinner than a human hair, and they embedded them within a sort of rubbery polymer substance. What they found that normally when dry, the material's quite stiff. The nanofibres are really glued to each other, but as soon as you introduce water, it separates the nanofibres, and the properties of the polymer start to dominate the composite so that it's soft and flexible. Now, they think that these sorts of materials could be used, for example, in the microelectrodes that are used as brain implants to help Parkinson's sufferers. Normally, you would assemble the components in dry conditions, so they're all stiff, easy to work with. But as soon as they get into the wet brain, they become soft and flexible, and that's one way that you could potentially reduce the scarring that you see in these sorts of implants.
So exactly how do we see this actually being done? Because they've had to physically go to these animals and get the fibres out, haven't they? So
no, this is the thing. This is kind of inspiration, but they're using exactly the same mechanism. So they're making their own nanofibres of cellulose. It's basically the same arrangement of thin threads packed into a rubbery, soft material. And depending on the conditions, the whole composite can either behave like a rubber or like a stiff CD case, in fact, is what they compare it to.
Just brain implants or other things as well?
Well, this is the thing. I mean, potentially, we spoke to a few scientists about this. A guy called Craig Hawker, for example, at the University of California, Santa Barbara, was so excited about this. He was gushing about it. And he was saying, why not think further? Why not do exactly what the sea cucumber uses this for? You can imagine a defensive suit that, under certain conditions, will become stiff and impenetrable.
Sounds handy on the streets of Cambridge, actually, Mark. Now, what about this last one, which is going to have people who are into their chips? That's French fries for our American friends. I'm looking at Mark Abraham sitting in the corner. Why should soaking them make them safer?
Yeah, back in 2002, people were quite surprised when a group of Swedish scientists came out and said that a chemical called acrylamide, which is thought to be a cancer-causing agent, was found really widely in baked and fried food. This happens because when you heat food like that up, there's a reaction that goes on between one of the amino acids in the food and the sugars in the food. The trouble is this is part of the browning process that generates flavour in all your roast vegetables.
Makes it taste great.
It makes it taste great. So the problem is, how do you get rid of it? Well, there's an enzyme that you can use to destroy the amino acid that's involved in this. And indeed, some scientists based in Denmark have now proved that you can do this to cut out a huge amount of the acrylamide that you normally get in this. Now, this is for the sort of manufacturers that would make ready-made oven chips. But in fact, scientists in Britain have also shown just last week that simply soaking chips in water before you cook them for a couple of hours can halve the acrylamide levels. There is a drawback, though. We talked to pretty much the UK's leading expert on acrylamide, Bronek Wedgicka at the University of Leeds, and he said, this is great, but the trouble is it's going to give you pale chips that lack flavour because the flavour reaction is so intrinsically tied to the reaction that makes this chemical, acrylamide.
I'm sure they can find something suitably carcinogenic to flavour them with afterwards, though.
I'm sure.
Thank you very much.
Thanks, Chris.
That's Mark Peplow. He's the editor of Chemistry World, which is the magazine of the Royal Society of Chemistry. They also have a wonderful podcast. You can find it online. It's the Chemistry World podcast.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Mm-hmm. Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
It's The Naked Scientists with Chris, Richard and Dave this week. We're taking all your calls on anything science. You can email chris@thenakedscientist.com. Now, the Ig Nobel Prizes honour achievements, it says, that make people first laugh and then think. And the prizes are intended to celebrate the unusual, honour the imaginative, and also to spur people's interest in science, medicine and technology. And as one major journalist put it, they come with little cash, but much cachet. And the guy who sorted it all out and started it going is Mark Abrahams, and he's with us. So, Mark, why did you start this?
let me correct something first. That business about they come with little cash. They come with no cash.
Okay, fair enough. But why did you get it going? What was the idea behind this?
I had become the editor of a science journal, and I discovered that when you edit a science journal, and I'm sure Mark found the same thing, suddenly all kinds of people get in touch with you, and they want to tell you about the wonderful things they've done. And some of those things are wonderful, some aren't. But you know that most of these people, no matter what they do, will never, ever, ever get any recognition from anybody. Now, I kept running into people who'd done things that were funny and interesting science, and it seemed a shame that nobody would ever know about it. And so that, more or less, is why we started the Ig Nobels.
The point about the Naked Scientist is when we try and have fun with science, because at the end of the day, if people are impressed as well as amused, they tend to remember, I think, and they'll also listen harder, I think, for longer. What do you reckon?
Yeah, I don't think that there's too much reason to try to bore people. I've never heard an argument in favor of that.
Let's take a look at some of the things that you've actually got on your tour and past prizes. I love the one about country music.
Yeah, we're going to be doing some shows in London, a couple of shows in London this week, and then in Newcastle on Friday night. There is a Professor Jim Gundlach from Alabama who, with a colleague, did a study about the effects of country music on suicide.
Mm-hmm. And?
He found that there may be some effects of country music on suicide.
Does it prevent or does it encourage suicide?
Well, the numbers are about 10 years old, so as to what will happen right now, which I think is what you're really getting at, no one can say. But what he found was that in cities that played a lot of country music on the radio, the suicide rates were a little bit higher.
Well, by all accounts, I mean, there is a very popular country show on this radio station, and it certainly does very well, and it's thriving, gets lots of calls, so the audience is certainly not dead. So who's killing themselves?
Nobody's tried to sue you yet.
Well, not me personally, but it's is it the people who are actually listening to the show who then are writing themselves out a death wish, or is it people who incidentally bump into some country music and aren't kind of habituated or prepared for it?
Yeah, if there's an effect, it's on people listening to music. It's not on people who don't listen to music.
Fair enough. Now, what about, because there was an interesting thing coming up in our question of the week this week, which is all about if you cut hair, does it grow more? Because there's this idea that if you cut hair, and often my wife says that she worries about sort of shaving her legs or something in case it makes them more hairy, and we're going to be looking at that in a second. But aren't people worried about pubic lice and things like that?
Of course people are worried about pubic lice. As soon as you mention it, people get worried. One of the people on the tour is Kees Moeilijker, who's from the Netherlands. He's the guy who won an Ig Nobel Prize a few years ago. He's an ornithologist. He won his prize because he documented the first known case of homosexual necrophilia in the mallard duck. But that's not why he's here this year. This year he's going to talk about a study done at Leeds by two doctors who said that in the past 10 years, the incidence of pubic lice in Britain have just fallen to almost zero. And the question is why?
Why?
And they have a theory. Their theory is that this is exactly the same time period when we saw a rise in popularity of that hairstyle known as the Brazilian.
Right, so it's just the absence of a suitable environment.
Yes, that's well put.
So, I mean, you can see the correlate of that in nature all the time, can't you? If you cut the trees down, don't any bears?
Yeah. Now, this has yet to be proven, and Kees is touring Britain partly because he's the curator of a natural history museum. Here we have a report of an imminently endangered species, and he's asking that anybody who has a living sample of pubic lice, please come to the shows, and he would love to collect it and take it to his museum.
The problem is, how are you going to conserve them? Because they only really like living on us.
One step at a time here.
Okay, so you're going to get the samples. Okay, then you look for suitable hosts.
While they're still alive. Could be urgent.
One person we had on the programme, must have been about a year or so ago, was Claire Rind, and she's a researcher at Newcastle, and she came to you guys' attention with the Ig Nobel Prizes because she showed locusts Star Wars and monitored their brain activity.
This is true. She and her colleague Peter Simmons, they monitored the activity of one brain cell in a locust while they had that locust strapped down and watching selected scenes from Star Wars. The scenes they were watching were in the original Star Wars movie. If you remember, the fighters dive into the trough inside the Death Star. And what they were wondering about was locusts typically are in swarms of tens of thousands, hundreds of thousands, maybe millions, but they seem not to collide very often. So they were wondering, what's going on inside the brain of a locust that helps prevent these collisions.
They did actually get quite a lot of interesting answers out, didn't they? And what they're now saying is that they could apply the neurological version of that to a robot to make more effective flying machines.
I believe they also got some funding from one of the large automobile manufacturers, too, who also are interested in preventing collisions, although they don't care that much about
come
locusts.
In handy on the roads in the UK, which are hopelessly overcrowded.
Mm-hmm.
Mark Abrahams, thank you very much. Just tell us, so that people can come along if they want to, where are the next set of shows, and how do they find out more if they want to come along and see
you can look at the schedule on www.improbable.com. The shows are Tuesday night at Imperial College, Wednesday night at the Guardian's little museum on Farringdon Street, Farringdon Road in London, and then Friday night in the Life Centre in Newcastle.
And they'll basically get yourself and some of these people we've been talking about.
A whole bunch of Ig Nobel Prize winners, and these are all free events, too.
And if someone wants to nominate someone...
Oh, please do. We're always collecting nominations. That's one of the best parts of the tour, is people come up afterwards and tell us about things they've discovered or people they know who've done things that need recognition.
Mark, thank you very much. That's Mark Abrahams. He's the guy who founded the Ig Nobel Prizes, and he's actually deigned to come from Cambridge, Massachusetts, here to the proper Cambridge in the UK to tell us all about it. It's part of his tour around the UK with his Ig Nobel Prize tour, which he does, I think, every year. Dave.
Now, coming up, we've got Diana with Question of the Week, but now it's time to hear from Rick Feinberg of Sky and Telescope magazine. Rick spoke to Mira this week about the latest developments in space. First up, Globe at Night, a project to bring together both professional and amateur astronomers with the public and get them all stargazing.
Well, one of the newest things that's happening right now is there's a worldwide effort on the part of both professional astronomers and amateur astronomers, and even among ordinary citizens, to measure the darkness, or actually the brightness, of the night sky to try to figure out what the impact of light pollution is around the world. When astronomers talk about light pollution, we're talking about artificial lighting that is wastefully being shined up into the sky and causing faint stars to disappear. Most people live in cities now, and they rarely get to see the night sky in all its glory.
And so what's the project actually getting people to do?
Well, the Globe Project is very simple. They ask people to go out at night in late February and early March and look at the constellation Orion, which is very familiar to most casual stargazers and which is visible from every point on Earth at this time of year, and count how many stars they can see in the constellation. And then they compare their view of the constellation with some templates that are on the Globe at Night website and determine whether they're seeing stars that are as faint as third magnitude or a fainter fourth magnitude or even fainter fifth magnitude. That's how astronomers measure star brightness. And that enables the Globe at Night project to do a worldwide map of sky brightness.
Has anything been revealed so far?
Well, this is the third year. In 2006 and 2007, they had something like 10 to 20,000 participants doing measurements. And they've been able to determine that measurements done from the ground by people track very consistently with measurements that are done by satellites in orbit, which is useful because if the information didn't match up, you might begin to suspect that your satellites weren't operating properly. As you might expect, most of the light pollution is clustered in populous cities. One of the things that's interesting is that it's possible, if you have a large number of people doing measurements in any particular city, is that you can find little enclaves where the night sky is a bit darker than surrounding areas, and these are places where amateur astronomers are likely going to want to go set up their telescopes because they'll be able to see more.
So that would be quite useful just for people to know their local best spot.
Right, and the Globe at Night project is planning to be much larger in 2009 because next year is the International Year of Astronomy. That celebrates 400 years of the telescope. Galileo first used a telescope to look at the stars in 1609. And the plan is to have a lot more people than have been participating in the Globe at Night project so far do it next year so that awareness of light pollution will be raised around the world.
Well, hopefully all will go well with the project and the number of astronomers out there will increase. But moving from the stars to the planets, it turns out that the liquid water that was thought to have existed on Mars wasn't there after all.
Well, NASA's plan for studying Mars is to follow the water. That's how they put it. Because if you follow the water, you follow lines of evidence that might ultimately point toward life on other worlds. And astronomers have seen lots of evidence that liquid water flowed on Mars in the distant past. We have huge canyons on Mars. We have things that look exactly like river deltas. So there's very little argument over the probability that liquid water flowed on the planet many, many years ago. We're talking millions or even billions of years ago. The question is there liquid water on Mars today? And in late 2006, using images from the Mars Global Surveyor, several planetary scientists saw evidence that liquid water can actually flow on Mars even now. What they saw was a couple of gullies that were cut into the sides of craters. And these gullies suddenly had fresh, light-colored deposits in them. And the thought was that between the time that the images were taken when there was no deposits and then when there was deposits, that liquid water had somehow erupted out of the gullies, probably from underground, and flowed down and dropped some salts or other deposits into these gullies, causing them to look different than they had a few years earlier.
And so what's happened to make them not think this anymore?
Well, now there's a much higher resolution camera in orbit around Mars on the Mars Reconnaissance Orbiter, and those craters that had the gullies in them were retargeted, and much higher resolution images enable planetary scientists to build a computer model that tries to explain how these gully deposits were laid down. And what they did was they now had really good three-dimensional maps of the gullies, and they simulated the creation of these light streaky deposits through liquid flow, through a mud flow or a lava flow, or through something more like a landslide, as if a hill had collapsed and all kinds of particles and dust and rocks had flown down. And what they found was that they could reproduce the appearance of these deposits in the gullies much more precisely using a dry flow, something like a landslide, than they could using a wet flow, as if there had been a flash flood in these gullies. So suddenly, the compelling evidence that liquid water has flowed on Mars as recently as the last few years is cast into doubt.
That was Rick Feinberg, Editor-in-Chief of Sky and Telescope magazine, talking to Mirror about the latest news about space research. If you want to get involved or see the results of Globe at Night project, then you can visit them online at www.globe.gov/GAN. Maybe you can find the best place near you for stargazing.
And here's someone who, well, we're talking about celestial bodies. Here's someone with a heavenly body. That's Diana. Hello, Diana.
Why, thank you. Hi, Chris.
Diana O'Carroll, who's here for this week's Question of the Week. What are we looking at, Diana?
Well, this week we've got a really hairy question.
Hey, this is Jay Rizal from Boone, North Carolina. And I was wondering if not cutting your hair and or washing it makes it grow any slower.
So, does how you treat your body fluff affect how it grows?
Unlike most other mammals, we have a very specific personal care and hygiene regime. Washing doesn't affect the hair growth itself, except perhaps some benefit you may get from massaging the scalp as you are washing the hair by ensuring optimal blood circulation in the scalp, which may have some positive benefit for the hair follicle itself. Shaving does not impact on the actual quality of the hair fiber produced, in that the hair is a dead entity above the surface of the skin. There is a perception of thickened hair regrowth, because if you were to cut it with a sharp instrument like a razor, you'll end up getting a sharpened end of the hair at its thickest point rather than at that tapered, more fine tip end. Well, hair growth is very, very important for the success of the mammal, and nature has provided enormous backup systems to ensure that the hair continues to grow, because in the wild you can imagine the loss of a coat would really be disastrous for a mammal in terms of thermoregulation or camouflage, etc. So as a result, the skin has invested enormous power into maintaining the hair follicle. And that's why it's so hard to get it to grow when you want it to grow, or stop growing when you want to stop it to grow. And that's because, well, the principal driver for hair growth is hormonal, particularly in those areas of the body associated with changed hair pattern after puberty. And there's a lot of clinical evidence to suggest that if you have abnormalities of the endocrine system or the hormone system, you can have altered patterns of hair growth, either too much or too little.
And that was Professor Des Tobin from the University of Bradford speaking there. So your hair should keep growing at the same rate no matter how much or little you wash and shave it. But an optical illusion on the hair shaft's end will make it look thicker if it's close cut. Massage may have an effect on hair growth, as JNA mentioned on our forum, but the main deciding factor is hormones.
Well, there was quite a debate on our forum as to whether or not hair stops growing when it reaches a certain length. Another underscore someone said it fell out once it got too long. UK Mickey linked it to follicles switching off and on. And Rosalind said it was all just down to genetics.
A whole range of answers there, thank you. Now, the moon can't make us into hairy werewolves, so here's a question on something it can affect.
My name's Roy Lightning, and I've got a question about the tide times. I often do a lot of walking, so I like to know when the tide is right out, because I like to walk out as far as I possibly can. But when I was looking at the Tide Times, I thought, how do they get it so accurate? It says something like, Wells Bar, low tide, 14:02. The question was really, how do they get it accurate like that? And who needs it that accurate? Because I certainly don't.
And following that one, we have a musical conundrum.
Hi, my name is Archana, and I'm calling from North Carolina, USA. My question is about accents. I've noticed that many people, when they speak in a language that is not their native tongue, usually have strong accents. However, when they try to sing a song in the same language, their accents seem to diminish. There are exceptions, of course, but this appears to be generally true no matter what their native language is or what language they try to sing in. Why is that?
So if you know why we tend to aspire to one singing accent, or why we need to know the exact time of high tide, drop us a line at questionoftheweek@thenakedscientist.com, or have a look at our forum. That's thenakedscientist.com/forum.
There you go, Diana. It's okay to carry on shaving. You're going to be all right.
Oh, yeah. Cheers for that.
It's The Naked Scientists with Dr. Chris, Dr. Dave, and also Richard Van Norden is here this week. And it's now time to find out the answer to that intriguing kitchen science that Dave had for you earlier. Dave, just give us a little roundup as to what you asked people to do.
I asked you to get hold of a really short piece of tubing, like a piece of hose pipe or maybe a marker pen lid, and 2 largish balloons. Blow one of them up so it's just starting to expand. Twist it off to keep the air in, put the other balloon over the end, and then let the air out and see what happens.
So hang on, so put the other balloon over the other end of the bit of tube, then untwist the balloon that you've got the air trapped in, and see what happens. So go on then. I mean, our prediction would be you just think it would equalise one on the other. Would you agree, Richard?
Yeah, I would think the air would move to the other balloon.
You get sort of a dumbbell-like thing.
Yeah.
Okay, go on, Dave.
Okay, so we'll do it. So
I'm totally overwhelmed by nothing happening, actually.
Yeah, it's somewhat more of a null result rather than an exciting thing happening.
It's really, really odd, because the balloon which you put all the air in to start with has stayed blown up, and the other one is just a little tiny bit blown.
Yeah, it's sort of blown up, sort of just so it's full. It hasn't stretched at all. And if I try and squeeze the air from the big one to the small one, it kind of squeezes across, and then at some point...
And then it starts to deflate itself.
Yeah, it suddenly starts squeezing air from the small one into the big one.
Without any more help from you?
Without any more help from me. I go back again, and the same thing should happen.
That's uncanny. So why is that happening?
Okay, so it's all to do. There's 2 things which are going on. You may have noticed that if you blow up a balloon, it's really hard to start blowing it. Then once you get beyond a certain point, it gets very easy. So what's happening is the small balloon is at the point where it's really, really hard to blow up, whereas the bigger one is in the point where it's easy. So the pressure in the big one is, because it's quite easy to blow up, that means the pressure must be quite low. So the pressure in the big one isn't big enough to blow up the small balloon, where it's really, really difficult. Now, the reason why this happens is 2 things. One is that rubber has got quite a strange thing. If you ever pull a rubber band, it's actually more difficult to stretch at the beginning than at the end. It gets difficult to stretch and it's easy and it's difficult. It gets easy again because as you stretch it gets thinner, so there's less rubber to stretch, so it's easier to stretch.
And that's why you're seeing this big balloon losing the battle against the small balloon.
Yeah, that's half of it. And the other thing is that if you've got something small, it tends to be much more curved. And if something's very curved, then if you pull on 2 ends of a curve, if you've got a piece of rope between you and me, and then Richard tried to pull it, if it's really straight, it's very hard for us to pull against him if he's trying to pull it sideways and try and bend that rope. So the pressure's so it's a bit like the air. It's going to be very easy to bend it, so it's going to be low pressure. But if it's very curved, it's going to be much easier for us to push against him, so there's going to be high pressure.
So how does this apply to the real world? Where would you see this manifesting in the world around us?
One thing is to do with the way foams develop, because foams are little bubbles of air, which are basically like a balloon, but with water on the outside, and water's got surface tension, so it's trying to compress these bubbles. And so small bubbles are at a higher pressure than big bubbles. So air inside small bubbles tends to move to big bubbles. So the bubbles in foam tend to get bigger and bigger and bigger until eventually get huge and the foam disappears.
I suppose one very obvious sort of analogue of this is in the human lung, because the air spaces, the alveoli, have to have surfactant, which is a chemical that stops the water from sticking to itself on their surfaces. Otherwise, they collapse very, very, very quickly when they're small, and this is a problem for premature babies because they don't have that surfactant.
So they're basically like really, really tiny bubbles, so they're trying to get smaller very quick, with very high pressure, trying to shrink them, yeah.
Is this a similar way to the way in which chairs that are pneumatic, like the one I'm sitting on, that you can pull the handle and it goes up and down? Is that how they work? Because with your added weight on it, it helps it to sink, but otherwise it comes up.
I think they've also got a spring inside them. So there's a spring inside a cylinder when you close the valve, and then there's air. It's sealed, so there's air in there. So if the valve is closed, then it acts as a strong spring because you've got air in there and the spring. When you let the valve out, then you just got the weak spring, so you can go down.
Thanks, Dave. I really enjoyed that. If you want to find out more about that experiment and how to do it and the science behind it, it's on our website at nakedscientist.com/kitchen science. Now, Nicholas is on the line. Hello, Nicholas.
Hi.
Welcome to The Naked Scientist. What would you like to talk about?
Well, I want to talk about dust because at this time of year the sun starts coming through the window and you can see that surfaces which you've dusted quite recently are covered with dust again, and you can actually see dust in the sunbeams. And I want to know where all this dust comes from. My dictionary defines dust as finely powdered earth, dirt, etc., lying on the ground or on surfaces and blown about by the wind, and that strikes me as being all very well for agricultural dust, but household dust is different. I can't believe it's all my epidermal cells.
I'm afraid, actually, it is, Nicholas. It's you and all the other people who have lived and visited your house. The stats really stack up, and they are really quite scary. The average human loses about 30 or 40,000 dead skin cells every single second, and if you were to add them all up and put them in a giant bag, over the course of a lifetime, that would weigh about 1.5 stone in dead skin alone. So most of that debris you see floating around in your house is dead bits of you floating around, and you're breathing that in, and you're breathing in bits of your partner, your family, your visitors, your friends. It's just bits of yourself.
Well, I'll just have to accept that, but even so, the figure you give of 1.5 stone or something like that is doesn't seem all that long in a period of 70, 80 years. Doesn't seem that much, I mean.
But a skin cell is very, very tiny.
Yeah, sure.
You're weighing a cell. The weight of a cell is measured with about 10 to the minus 9 zeros in front of it in terms of its kilogram mass. I mean, it's tiny.
But when you see a particle of dust, that's not one skin cell, is it?
No, they're normally clusters, so these things get stuck together, and other fats and materials that are present with them stick them together, and as a result you end up with something that forms a blob of dust.
Okay, well, I'll just have to accept your word for that, and it's a totally disgusting thought, which I'm glad to have shared with all your listeners.
Well, thank you, Nicholas, for that wonderful question. Right, Richard, I've got an email here from Dwayne, and he says, I'm curious to know if our fizzy drinks are adding significant CO2 to the atmosphere. Think about all the soda that gets served up every day. It's sure to add a significant amount of escaped gas. Additionally, what happens to the CO2 once it's inside the body? The CO2 must go somewhere or be released eventually. Could we slow down CO2-linked global warming just by using drinking water instead of carbonated drinks?
Well, you're absolutely right. All the CO2 does escape from the fizzy water, whether it's in your body or straight away, but don't worry about it, because where has that CO2 come from? It's come from the waste streams of power plants, so it's a byproduct, essentially. It's not extra CO2 which is being produced for the fizzy drink. It would have gone into the atmosphere anyway. But using any consumer product like fizzy drinks obviously takes a lot of manufacturing, takes a lot of shipping to get the fizzy drink to where you are. And that's what's going to require us to use fossil fuels and get CO2 into the atmosphere. So really giving up fizzy drinks and turning to tap water might help to stop global warming, possibly not in the way that you thought.
Thank you, Richard. Well, here's something we can all speculate about, because it's an email from Kevin who says, in theory, might it be possible to engineer a type of airborne microbe or virus that could be released into the atmosphere where greenhouse gases are highly concentrated? These microbes will be designed to feed off the gas but expel harmless gas as a byproduct. What do you think of that?
Well, I don't know about an airborne version, but we do already have microbes which do this. They're called algae in plants. They feed off the carbon dioxide. They need sunlight to do it, and they give out oxygen. Unfortunately, at the moment, they're not feeding off it enough, and they're not getting rid of all the extra carbon dioxide we're putting into the world.
Because those algae are largely in the sea, and the sea is accounting for over a third of the absorption of the CO2 that we've put into the atmosphere. So they're doing quite a good job. But they're not obviously fixing all of that. It's just dissolving in the sea. But obviously they could in the long run.
And also, of course, even if you do get algae growing, then something will go and eat the algae and burn all of the sugar and the carbon inside them.
And the CO2 comes straight back out again as gas back into the atmosphere. So actually there's no real big solution apart from just to produce less CO2, I guess.
Unless you can grow lots of algae and make it sink to the bottom of the ocean and get buried.
Yeah, there's been some recent experiments trying to do this, but unfortunately a problem with all of these ideas is something of this scale, a huge geoengineering project, very dodgy to know exactly what's going to happen.
Thank you very much, Richard. Right, well, that's all we've got time for this week. It just remains for me to say do join us next time when it's the Cambridge Science Festival, so we'll have an update on the best of the fest for you here on The Naked Scientist. But let me thank very much the guests this week, Mark Abrahams, Mark Peplow, Rick Feinberg, and also our wonderful production team, Mira Senthalingham, Ben Vausler, Diana O'Carroll, who handles Question of the Week, and Petro Minch, and our wonderful co-production presentation team here in the studio, Dave Ansell with his Kitchen Science, and Richard Van Norden. Do join us next time. More on the web at nakedscientist.com. Thanks for listening. Goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.